Modern digital design looks simple on the surface. We draw schematics, route traces, and expect signals to behave like ideal ones and zeros. But at high speed, signals don't behave like symbols. They behave like electromagnetic waves. As clock frequencies increase and rise times get shorter, the physical design of interconnects starts to dominate system behavior. PCB traces, vias, packages, connectors, and even power planes stop being passive wiring and start becoming part of the circuit itself. This is where signal integrity comes in. In this series, we're going to build an intuitive and practical understanding of signal integrity, power integrity, and their relationship to electromagnetic compatibility. We'll focus on why signals distort, where noise comes from, and how physical design decisions directly affect performance. Rather than memorizing a long list of problems, ringing, reflections, crosstalk, ground bounce, rail collapse, we'll learn how these effects all come from a small number of underlying principles. Every episode in this series is based directly on the concepts and explanations from signal and power integrity. Simplified by Eric Bogatin, with the goal of turning complex behavior into engineering intuition you can actually use in real designs. If you design PCBs, work with high-speed digital systems, or want to understand what's really happening on your signals, this series is for you. Let's get started. Signal integrity is in your future. Signal integrity is no longer a niche topic. As Eric Bogatin puts it, there are two kinds of engineers: those who have signal integrity problems and those who will. Modern electronic design is moving toward higher clock frequencies and shorter rise times, while development schedules are getting shorter. Design teams often get only one chance to get a product to work correctly. If signal integrity problems aren't identified and addressed early, the chances are high that the product simply won't work the first time. Why signal integrity matters. We're in an era where clock frequencies are increasing and signal integrity problems are becoming more severe. At the same time, design teams have less time to solve these problems before releasing a product. Successful companies are the ones that master signal integrity issues and build efficient design processes that eliminate these problems early. Signal integrity is no longer optional. It's critical to product success. Physical design affects signals. This figure shows a 100 Hz clock waveform from a driver chip. When there's no PCB trace connected, the waveform looks clean and smooth. But when only a 2-inch PCB trace is connected to the output, the waveform shows ringing and distortion. This demonstrates an important idea. Even a very short PCB trace can significantly affect signal quality. At high speeds, the interconnect itself becomes part of the electrical behavior of the signal. When interconnects were transparent. In the early days of digital design, clock frequencies were around 10 MHz, and rise times were on the order of 10 nanoseconds. At those speeds, even crude interconnects worked fine. The electrical properties of traces and packages didn't significantly affect system performance, so we say the interconnects were transparent to the signals. Enter the high-speed regime. As clock frequencies increased and rise times dropped below about 1 nanosecond, this situation changed. In this high-speed or high-frequency regime, interconnects are no longer transparent. The physical design of traces, vias, planes, and packages directly affects signal behavior. If we're not careful, signal integrity problems will appear. What is signal integrity? Signal integrity refers to all the problems that arise in high-speed products due to interconnects. It's about how the electrical properties of traces, packages, and return paths interact with the voltage and current waveforms of digital signals, and how that interaction affects system performance. Power integrity and EMC. Power integrity deals with noise in the power distribution network, everything from voltage regulators to planes, vias, package leads, and decoupling capacitors. Electromagnetic compatibility, or EMC, deals with radiated emissions leaving the product and susceptibility to interference from the outside world. When we talk about problems, we often say EMI. When we talk about solutions and compliance testing, we usually say EMC. SI, PI, and EMC overlap. All three, signal integrity, power integrity, and EMC, must be considered together for a successful design. There's significant overlap, especially between SI and PI, because signal return paths often use the same interconnects as the power distribution network. This overlap can cause confusion because problems may fall into a gray area where different engineers each think it's someone else's responsibility. Noise problems versus timing problems. In the signal integrity domain, problems generally relate to either noise or timing. Noise can cause false triggering or bit errors, while timing issues can violate setup and hold margins. Although timing budgets themselves aren't covered in detail here, the effects of interconnects on rise time distortion and jitter are covered extensively. The explosion of SI terms. We hear many terms related to signal integrity: ringing, reflections, ground bounce, crosstalk, attenuation, non-monotonic edges, and many others. At first glance, this looks like a random and overwhelming list of problems. It can feel like there's an unlimited supply of new effects to worry about. 6 families of problems. In reality, all signal integrity, power integrity, and EMC problems fall into just 6 families. These include signal distortion on one net, rise time degradation from losses, crosstalk, ground and power bounce, rail collapse in the PDN, and electromagnetic interference. Once we identify which family a problem belongs to, the general solution becomes much more obvious. What is a net? A net includes all metal connected together in a system, not just the signal path, but also the return path for the signal current. Figure 1 foreshows 2 example nets on a circuit board. Even though the routing looks different, all connected metal belongs to a single net. Both geometry and return path matter. Reflections and impedance. Changes. When a signal leaves the output driver, it sees the interconnect as an electrical impedance. If the impedance the signal sees stays constant, the signal remains undistorted. But if the impedance changes, part of the signal reflects, causing distortion that can bounce around the interconnect. Impedance, discontinuities. Any feature that changes the geometry or return path creates an impedance discontinuity. Examples include the end of a trace, width changes, VS, gaps in return, planes, connectors, and routing branches or stubs. Every discontinuity causes some amount of signal distortion. Ringing and termination. Figure shows ringing on an unterminated line and good signal quality when a source series termination is used. What we often call a ringing is really the result of reflections caused by impedance changes. Termination works by managing the impedance at the ends so the signal doesn't see a sudden change. Routing topology matters. Even with good termination, poor routing topology can still cause reflections. When a trace branches into multiple paths, the impedance at the junction changes, and part of the signal reflects back while the rest continues in a distorted form. Daisy chain routing restores a constant impedance and improves signal quality. Why rise time is critical. This figure shows that a discontinuity that wasn't a problem at a 3 nanosecond rise time becomes a serious problem at a 1 nanosecond rise time, even at the same clock frequency. As rise times get shorter, impedance control becomes more important everywhere, including inside packages. Crosstalk basics. Crosstalk occurs when voltage and current from an active net couple into a nearby quiet net. This coupling happens through both capacitive and inductive mechanisms, which can also be described as fringe electric and magnetic fields from the aggressor line to the victim line. Near-end and far-end crosstalk. Figure shows measured near-end and far-end crosstalk. In this example, the near-end noise is about 7% of the signal, while the far-end noise is nearly 30%. This highlights how significant crosstalk can become in high-speed systems. Return paths and switching noise. A wide, uniform return plane produces the lowest crosstalk. When the return path is disrupted, such as in connectors or packages where multiple signals share a single return pin, inductive coupling increases dramatically. In this case, crosstalk is often called switching noise, ground bounce, or simultaneous switching noise. Ground bounce example. Ground bounce is a special case of crosstalk caused by high mutual inductance when return currents overlap. Figure 1.8 shows switching noise appearing on a quiet line due to mutual inductance between active and return paths in a package. Rail collapse noise. Noise doesn't only affect signal paths, it also affects power rails. When currents switch in the power and ground distribution network, voltage drops appear across the impedance of the PDN. Reactive elements and resonances can produce large voltage spikes. Rail noise causes jitter. Changes in power rail voltage affect gate switching speed. Higher voltage makes gates switch faster, pulling clock edges in. Lower voltage slows gates down, pushing edges out. This variation in edge timing is a dominant source of jitter. Rail collapse example. Figure shows measured VCC voltage at 3 pins of a microprocessor just coming out of a stop clock state. Although the nominal voltage is 2.5 volts, voltage drops of nearly 125 millivolts are observed due to impedance in the power distribution system. PDN impedance trend. This figure shows the long-term trend in the maximum allowable impedance of the power distribution network for high-end processors. Over time, allowable PDN impedance has dropped dramatically, making low-impedance power delivery increasingly difficult and increasingly important. Designing a low-impedance PDN. To reduce rail noise, the most important design practice is to engineer the PDN as a low-impedance system. This includes closely spaced power and ground planes, multiple low-inductance decoupling capacitors, short package leads, low-impedance voltage regulators, and on-package and on-chip decoupling. Key takeaways: signal integrity, power integrity, and EMC are all consequences of the same physical reality, the behavior of interconnects. By classifying problems into a small number of families and understanding how impedance, return paths, and rise time affect signals, we can design systems that work the first time, even at high speed. That wraps up this episode of the Signal Integrity series. Everything you've seen in this video is based directly on the concepts and explanations from signal and power integrity. Simplified by Eric Bogatine, with the goal of building real engineering intuition, not just rules to memorize. If you found this useful and you want more content like this, make sure to subscribe to the channel. Here I regularly cover signal integrity, PCB design, and basic electronics theory, all focused on understanding how things actually work, from schematics all the way down to the physical layout. In the next episodes, we'll continue building on these foundations and go deeper into how interconnects, return paths, and impedance shape signal behavior in real designs. Thanks for watching, and I'll see you in the next one. Let's get started.